So we want to identify now what I'm going to call third law pairs. Third law pairs are pairs of forces, two forces that exemplify or exhibit or show Newton's third law. Remember, Newton's third law says if you have two objects interacting with forces, with pushes or pulls, if object A applies a force on object B will apply a force of equal size back to object A. So, do I have any third law pairs in my diagram so far? I want to give you a second. Think really hard about this. Think about Newton's third law. Think about the diagrams, all the forces that are happening, and see if you can answer it. Yeah, I do have a third law pair. It's right here. I'm going to label it. I'm going to label the forces in this pair with a green star. It's these two forces right here. Let's talk about why these are a third law pair. Remember, Newton's third law says that if an object exerts a force on another object, that object will exert an equal force back. So think about it. We said that the book was being pushed up by the table. So the book is feeling a pushing force by the table up. So what does the book do in return? By Newton's third law, the book must push the table down. That has got to be the case. This is a third law pair. Something to note that will help you with third law pairs is third law pairs will always be on different objects. A lot of people are tempted to say that this force going up and this force going down are a third law pair because they cancel each other out, they're equal and opposite. That is not the case at all. It is true that these forces cancel, they balance, they're equal and opposite. In our example here, it was plus 5 and negative 5. Remember the plus and negative show direction, so opposite direction, same size of 5, equal and opposite. But these are not third law pairs. This is a contact force. This is a gravitational force. This force is coming from the table. This force is coming from the earth. So these two are not a third law pair. These two are. Your third law pair will always be on separate objects. So the table pushes the book up. What does the book do in return? It pushes the table down. And if we're really careful, we should show our entire diagram so that these two arrows here are equal to each other. My diagram is not that great. Some people like to add little hash marks like this to show that forces are supposed to be equal to each other. I don't care if you do that. I'm not going to do that. I think that the star here shows enough that that my forces are equal to each other. Equal but opposite forces exerted by objects onto each other. This is the diagram for the book. The table pushes the book up. This is the diagram for the table. The book pushes the table down. The table pushes the book up. In turn, the book pushes the table down. That's a third law pair. Are we done? No. I'm trying to do force diagrams for the whole system. So I have the book, the table. Now I need to do the earth. Let's think about this. Should I show the earth having any downward gravitational force? No, the earth is not attracted by its own gravity. It is attracted by the gravity of the sun, things like that, but the sun is not in my system, so I'm not really going to worry about that right now. So what am I going to show? Well, is the earth being pushed down by anything? Yeah, think about this. Look at this over here. The earth was pushing the table up. So what does the table have to do? Newton's third law, what does the table have to do? It has to push the earth back down. So I'm going to say this is a contact force felt by the earth, dealt by the table. The earth pushes the table up. The table pushes the earth down. Guess what I have, ladies and gentlemen? I have another third law pair. The force of contact felt by the table, dealt by the earth pushes the table up, the table pushes the earth back down. There is a second third law pair. Do I have any other forces acting on the earth? I want you to think very carefully about what we've said. If object A applies a force onto object B, then object B will apply a force of equal size back. Think about it. These gravitational forces, the earth pulls on the book. The earth pulls on the table. By Newton's third law, what must the book and the table do back to the earth? they must pull as well. Remember in our discussion about gravitational forces that gravity is an attractive force between masses. If you have two masses, they pull on each other gravitationally. So we think about gravity all the time as being us and all of the objects on the Earth drawn toward the Earth. But guess what? The Earth is also drawn towards us. So the Earth does experience a gravitational force upward, the force of gravity, felt by the Earth, dealt by the book, and another force upward, another force of gravity, felt by the Earth, dealt by the table. This freaks people out because people always forget about this and they think that, oh, of course the book doesn't pull up on the Earth. Of course the table doesn't pull up on the Earth. That's how gravity works, ladies and gentlemen. It's an attraction between masses. So right now you are pulling the Earth up a little bit. Why is the Earth not coming up and accelerating up towards you if you pull on the Earth? Because the force of gravity is very small and it's only really felt and it's only significant for objects of very large mass like the Earth. So you are pulled towards the Earth very strongly because the Earth is very, 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 very massive compared to you. But the Earth is not pulled up to you gravitationally very strongly at all because you have such a tiny mass compared to the Earth. But the force is still there. Even gravity has to obey Newton's third law. If the force of gravity dealt by the Earth is felt by the book, then guess what? The book is going to pull gravitationally back on the Earth. There's another third law pair. Do we have another one? We sure do. If the Earth pulls down on the table gravitationally, then guess what? The table has to pull up on the Earth gravitationally. This is a force diagram. We have represented every object with a dot, and we've thought very carefully about the pushing and pulling forces acting on every object. We've tried to draw our arrows to show if there's a net force or not. The book is at rest. It is not accelerating, so it has no net force. These forces have to cancel out. They have to be balanced. We call those balanced forces. The table is at rest, so all the forces there must be balanced. So you always want to think about the size of your arrow. You want to think about the direction. Force is a vector. Then you're going to label each force with a feeler and, label each force with a type, feeler, and dealer. Types of forces can be gravitational, contact. If you're dealing with string, sometimes we call the force from a rope or a string, we call that we call that tension forces. And you're going to label them with the feeler or dealer. What's feeling the force? It's always going to be the object you're analyzing. What's dealing the force? What was pulling the book down gravitationally? The Earth's mass. What was pushing the book up? Contact with the table, feeler and dealer, felt by the book, dealt by the table. Remember to always draw your arrows with the tail on the dot, never ever the tip of the arrow on the dot. And once again, make sure that you're showing that the forces are balanced. In fact, if I wanted to show very clearly that these forces are balanced, I could add to my diagram this little notation. I could say, hey, the sum of these forces is 0. Same thing for this diagram. The sum of these forces is 0. The sum of these forces is 0. Just to make it clear that these forces cancel out. They're vectors. I don't have anything left over whenever I add them. I go up 5, I go down 5, I'm back where I started. The net force is 0. We'll talk more about that in a bit when we analyze Newton's second law further. For now, why don't you do a final example of Newton's third law. A skydiver is falling to the earth. I would like for you to draw a free body diagrams for the system before he deploys his parachute and after he deploys his parachute. Let's say after he deploys his parachute, his acceleration equals 0. So here's the Earth, here's the skydiver is falling down, and this is my system. So here's before the parachute. I'm doing the whole system. Well, what's in my system? The skydiver and the Earth. So let me start with the skydiver, represented with a dot. Here's the skydiver before the parachute. Before he deploys his parachute, some of you are familiar with this word, air resistance or draft. So technically speaking, there is some air resistance as he's falling, as the skydiver's body is falling. It's bumping into all these air molecules, which are kind of, through collisions, applying an upward force onto the skydiver. That's draft or drag or air resistance. Before the parachute, we're going to ignore air resistance. So what is the force acting on the skydiver? Force of gravity, going down. Force, the type, the feeler felt by the skydiver, the dealer. Where's that force of gravity coming from? The Earth. What other object is in my system? The Earth. Does the Earth have a force on it right now? Considering all the objects in my system, it sure does. It has a force of gravity felt by the Earth, dealt by the skydiver. Remember, gravitational forces are always attractive between objects. Guess what I have here, ladies and gentlemen? I have a Newton's third law pair, don't I? So this is what the diagram would look like before the skydiver deploys his parachute, ignoring air resistance. Let's draw it after the parachute. Here's my skydiver. I want you to think about this. After his parachute deploys, his acceleration is 0. I should have mentioned over here, is the skydiver going to be accelerating? Yes or no? Yes, the skydiver is going to be accelerating. How do I know that? Because look at this force vector. Does it have anything opposing it? Is it being canceled out by an upward force? No. It just goes down. I do not have anything canceling it out going back up the other way. I don't have an upward force at all. So I have a downward net force. Remember, Newton says that if you have a net force, what is that going to result in? An acceleration. If you have a number over here, you're going to have a number over here. In the examples we saw before, the acceleration was 0, so the net force was 0. All the forces were balanced. This is unbalanced. This skydiver is experiencing a change in motion. A net force, an unbalanced force, causes a change in motion. A total overall force causes acceleration. So guess what? This skydiver is accelerating downward. So maybe I could say this. Maybe I could say that the net force here is greater than 0, and the skydiver is accelerating downward. Let's do after he deploys his parachute. We know that the acceleration is 0 now. So we know that the net force is 0, the acceleration is 0. Does that mean there are no forces acting on him? Does that mean that the gravitational force that was acting on him somehow disappeared? No, he's still near the surface of the Earth. He's still experiencing that exact same gravitational force. This has not changed at all. Gravitational force felt by the skydiver, dealt by the Earth, it's the exact same as it was. What has changed? He's deployed his parachute. The parachute greatly increases his surface area, increasing the collisions with air particles, increasing the upward force that he feels. So now there's a large force up. I'm going to call that a force of air resistance or a force of drag. It's really just another type of contact force, collisions between objects. Let's call it a force of air resistance felt by the skydiver, dealt by you could say the parachute, you could say the air, whatever you want to say here. I'm going to say dealt by the air. A force of air resistance felt by the skydiver, dealt by the air. These arrows must be the same size. The net force has gone to 0. The downward force of gravity is now completely canceled out by the upward force of the drag, and so the net force is 0. And we still have the Earth. Has anything about the Earth changed? No. The Earth is still pulling the skydiver down gravitationally, and the skydiver is still pulling up on the Earth gravitationally. So we could also, on this diagram, mark our third law pairs with a star, and there you are.